Good morning, everyone. Welcome to today's lecture, and thank you for coming to be here. And we also send our greetings to our audience in the Zoom meeting room. And my name is Merapi, and today I will be moderating this session, today's session. And today's lecture focuses on the origin and mechanism of volcanic eruption, particularly for caldera forming eruption, as well as the associated volcanic hazard and mitigation strategies. And our goals in today's lecture is to better understand how to live safely and in harmony with the volcanoes. And this event is organized by the Environmental Geomorphology and Disaster Mitigation Laboratory from Januari University in collaboration with the Volcanology Research Group at Ibaraki University. And today's lecture will feature 3 speakers. Each speaker will present for approximately 30 minutes, followed by a short question and answer session after each presentation. And we have some souvenirs from Japan for those who give interesting questions for each Q&A session. So please don't hesitate to ask questions. And
University, and last time is September. So I already gave general topic of Japanese volcano and its hazard and mitigation. So today I'd like to talk about more specific topic. So about how complex calderas form. So, and I will show you the case of Akan caldera in Eastern Hokkaido, Japan. So at first, you can see the beautiful bird. This is tancho, we call tancho in Japanese language. So this is a crane in Japanese bird. So and they live in Eastern Hokkaido. So more than 100 years ago, this bird almost was extinct, but now people protect for conservation. So now we can easily watch this bird. So the tancho is a Japanese symbol, and this is designed for Japanese banknote, 1,000 yen, JP yen, and this this is a symbol of long life and happiness. So if we can see the tancho in the field work, so we feel very happy, and so my field work goes well. So this is my favorite bird in Japan. Okay, so let's move on the scientific topic. So my specialty is volcanology, and especially in caldera volcano. So at first, let's review the definition of caldera. So normally, our general image for volcanoes, just a mountain like this. This grows upward. So we call this stratovolcano, like Merapi and the other stratocones. but caldera volcano is inverse, so growing downward. So this is a very simple illustration. So this shows caldera volcano ejected a lot of magmas for a short time, and after the evacuation of the magma underground, so the roof rock subside, collapse to make the huge crater. This generally the diameter of caldera is more than 2 kilometers. This is the definition of caldera. So I like caldera. We call inverse volcano. So as I said, so before the huge eruption, very large scale magmas existed under the volcano, and so more than 1 cubic kilometer, sometimes more than 100 cubic kilometer magma ejected shortly, and after that there makes the space in the magma chamber to make the collapse, caldera. So this is Nova Sensei's achievement. This is about Sumatra caldera. So generally speaking, so we can recognize a lot of very wide and thick pyroclastic materials around the collapsed caldera. So like pyroclastic materials such as pumice and ash. So we study this kind of materials, pyroclastic deposit, to reveal the formation history of caldera. So pyroclastic materials can be categorized two things. So one is ignimbrite. This is a pyroclastic flowing on the ground, and another one is pyroclastic airfall, falling from the air. Okay, so let's start about Akan caldera in eastern Hokkaido. So, ごめんなさい. Sorry. Okay, I move this way. So, okay. This is a north part of Japan. I don't know, have you ever been to Japan or not? So you come to Japan next month. So this is Hokkaido Island, the north part of Japan. And this is the eastern part of Hokkaido. So as you can see, there are a lot of caldera topographies. So we call this caldera cluster in eastern Hokkaido. So at least 3 caldera volcano we can recognize, and a lot of pyroclastic materials shown by pink pattern, so we can recognize and observe. So the west one is Akan caldera, today's object. And this is Cucciaro caldera. This is the largest one in this cluster. And this is small one is Mashu caldera. This is the youngest. Hi. So among this caldera cluster, so the age of the formation of calderas getting more younger from the west to east. So let's have a look at the caldera pictures from the youngest one, Mashu. Hi, very beautiful lake. We call this caldera lake Lake of God in Hokkaido. So this is just a crater, less than 2 kilometer diameter. So this is a caldera, Mashu caldera. Diameter is about 8 kilometer. So it formed Holocene 7.6 Ka. This is a Kucharo caldera, the largest caldera in Japan. So you can see some post-caldera volcanoes inside and a beautiful lake. Right. Next. So the younger two caldera shows, you can see normal circular shape like this, very round shape here. This is normal caldera shape. But as you can see, Akan caldera, the oldest one, is not normal, not a simple circular shape, but rectangular complex shape. So next view is from this side to northeast. So this is a view of Akan caldera. So it's difficult to recognize the caldera wall. Where is caldera wall? And this is a caldera lake, but very small. And this one is post-caldera volcanoes. There are a lot of post-caldera volcanoes grown inside of the caldera. And by the way, so Akan caldera. Oh, okay. Akan Lake. This is Lake Akan. Very small but very famous in the world. So in Akan Lake, so we can get the very special plant, a kind of seaweed, marimo. This one, round a kind of algae plant. So the marimo grows only the environment of very cold and clear lake water. So this is very rare species in the world. Okay. Anyway, so Akan caldera is my caldera. So that means, so I study Akan caldera from my undergraduate student. So I study this caldera for more than 20 years. My home. I love Akan caldera. So. And this is the first outcrop I came. So when I was an undergraduate student, so my supervisor said, go. You must go to the field alone. So, oh, sensei, can you come together with me? No, you go alone. So, very strict professor. And but he kindly taught the best outcrop, this outcrop. So I went to this outcrop, and at that time I had no knowledge of volcanology. So my first description of this outcrop is lava flow. Lava flow. It looks very hard rock, lava flow. This looks ash and pumice, but so I was thinking, oh, this is pumice lava. So, but so when I approach, when I touch the outcrop, so I realized that. So, oh, this is not lava flow. Oh, ash, pumice, gradually changing to hard rock, solidified rock. So this is welding of pyroclastic flow. So, okay, this is not welding. So welding is welding occurred when the hot pyroclastic materials over the temperature over 600 or 700. So pyroclastic deposit empressed at hot condition, and it compaction for the weight itself, and hot condition makes the pumice sticks together, and resulting to welding tough. So it's very hard rock. So I was so impressed. Oh, this is a welding, and this is evidence, not lava flow. So we can clearly recognize ash to welding. Okay. So, and this outcrop is in front of the farm, dairy farm, milk farm. So, at that time, so I had no fundings for staying at the field for a long time. Next slide はできるかな? Next. How to? Okay. So I had no money for long stay in the field. So, and I asked to the professor, oh, do I have funding? No. So I asked to the people who lived in the field. So one by one. So I asked, can I stay here? It looks a little bit crazy, but so but one kind person, one kind farmer, Nakao-san, so he kindly accept me, and so instead, so you have to help, you have to work here in the early morning. So, and so daytime I did field work, and in the morning I built. So, this is great memory. And so I stayed in the farm totally more than 1 year, 2 years. So, and at least 3 months at one trip. So, and in summer season, so they asked me, so please join to the rock music band. This is not rock, just rock band. So, and I was a vocal. So this is myself. Yeah. So looks young. A lot of hair. So, I lost my hair, but I got professor position now. So, おめでとう、ありがとうございます。Congratulations. So, and and this is Nakao-san's farm. So, this is my wife. At that time, not wife, of course, but so I got my wife at the field. ですね。そうそうそう、思い出します。So if you work field work hard, so you can get your wife and husband ね。はい。OK。あれ。おは、more 15 minutes? Halfway? More 10 minutes. Okay, okay. Okay. So, okay. So, and I found a lot of good outcrop where I can recognize a lot of layers at the same time, like this. So, and I described, I described the pyroclastic layers one by one between soil layer. So soil layer means that is a period of no eruption. So we divide the ash layers by soil. Oh. ね。あ。ちょっと待って。うん。Difficult to, slide work is a little bit difficult. Okay. Okay, okay. Thank you. So, and I established the Akan stratigraphy like this. So totally 17 units from Akan caldera. So a lot of very, very large amount of tephra layers. And younger, at the latest stage, the Akan caldera forming eruption interfingered with Cucharo caldera eruption. So Akan caldera eruption, Cucharo caldera eruption, Akan, Cucharo. So we rebuild. これ、あ、OK, OK. I try. This is better. Maybe. 野場さん、can you? ね。できないね。OK. OK, OK. And I established the stratigraphy, but we had no age constraint, no dating data. So, and I couldn't do radiometric dating because no enough potassium. Potassium is necessary for potassium argon dating, and no zircon crystals. Zircon is necessary for uranium lead dating. So, and as you know, no funding. So my professor couldn't pay for the dating. So my professor is very nice and very. I'm so appreciated my professor, but so at that time, so what a strict professor. ね、ちょっと難しいね。Okay. And in this situation, I found exotic tephra. Exotic means the widespread tephra, not from Akan volcano, but from far area, from central Hokkaido, more western side. And these tephra layers contains a lot of potassium, biotite, and zircon. So a lot of good data for this exotic tephras. So I introduced these tephra ages to Akan stratigraphy because I found these time marker tephras. So, and we realized, we revealed that the activity, the life of caldera is very long, very, very long, longer than Cucharo Machu, so more than 1 million years. Okay, let's skip. And this is the final topic. So, and our final question is, a very long history and very lot of many eruption units. So these eruptions from single source, single vent, or multiple vent. So for this question, so I focused on the accessory lithik fragment. This is not essential. So essential material is ash and pumice. That is solidified magma at the eruption. But the lithik fragment is old rocks around the crater. So the eruption, magma ejection, tomb broke the rocks around the crater and incorporate the lithik fragment. So we analyzed the lithik fragment for each unit. And so we revealed that this pink one is largest unit after largest unit for young stage. So AK742, the not pumice, but lithik fragment type are really different between these three units. That means bent area, bent geology were different between these three units. So 3 bent areas we recognized. And after that, I did geophysical research. So this is a Bugge gravity anomaly map. So if there is light, soft materials inside the caldera, the gravity anomaly will be low because of light, not heavy materials. So, and we did the gravitational survey with my collaborator, geophysicist, and we revealed 3 distinct low gravity center here. So this is very different from Cucharo caldera. Cucharo caldera is very simple structure, so one big depression. But the Akan caldera consists of 3 different small depressions. So this is very consistent with 3 different vent area. So, my supervisor finally will be happy. It's good story. So you can get PhD finally. So, and this is a really final question. So different magma, different eruptions from one single magma system or small different magma systems. So, and this is the answer. So different. So 3 different vent area is a source of 3 different small magma chambers. So you can see 3 distinct chemical trend this is SiO2, this is potassium. So this chemical, this is magmatic chemistry, magma chemistry. So it's not interaction, each other. So this is different. So well, 5 minutes or something, few minutes. Okay. So this is a conclusion of my study for Akan caldera. So we constructed detailed stratigraphy for Akan caldera forming eruptions, and totally it's consists of 17 units, and younger 7 units are largest. That might to decide the main shape of caldera, younger units. And based on lithic fragment analysis, we recognize 3 different bent areas. And based on gravitational survey, 3 depressions, and that are derived from 3 different magma systems. So very good story we constructed. So this is a final illustration of the model. So, okay. So AK7 erupted at 0.8 MA, 800 Ka. So the eruption derived from this green magma chamber. So different magma chamber erupted from it is more eastern side of the caldera. Central. And next stage, AK4 erupted from eastern side of the caldera from different, this is blue, medium potassium content magma. And finally, from the western side, the largest eruption happened from the highest potassium magma. And finally, it made very complex, not circular, complex caldera. And this result published in my frontier paper. So you can this is free access paper, so you can read anytime. So if you are interested in. Okay, this is my talk, and what I want to say is complex feature, maybe it's common for volcanoes. So I study Mar volcano in Cameroon with Aka Sensei, next speaker. So this is a Mar volcano in Cameroon. This is Lake Manun Mar. So generally speaking, so Mar volcano is monogenetic. So just one eruption makes the one crater. But in this case, we recognized at least 3 craters and 3 different units with my student and Aka Sensei. So this is my result. This is not caldera, but Mar. But I think this kind of very complex, multiple future of volcanic vent, magmatic system may be common in the world. That's all. Thank you very much.
Thank you very much, Hasegawa Sensei, for the fun and interesting talk. So we have time for 1 or 2 questions, and we accept 1 question at a time. So has anyone? Oh yeah, we have also souvenirs from the Geological Society of Japan for anyone who asks questions. Okay, okay, so please introduce yourself first and then give a brief question.
Hello, Sensei. My name is Faris. I want to ask question about the AK-13 unit. Yes. You mentioned in the lithic content in the graph, AK-13 have also many lithic content, but how about the AK-13 position from the three others group?
Very good question. Can I go back? Right? Good question. So I did componentary analysis for listic fragment for all unit, but the older unit, it's more difficult to identify the rock types and not so clear difference from the younger unit. So, and yes, AK-13 is one of the largest unit, and this shows very unique chemistry to here. Very unique, relatively high potassium chemistry. It's and the other unit is white material, but this is black material. So very unique and large. So to simplify the story and my logic, so we I focused on only younger unit that that defined the present shape of the caldera. But so as you say, AK-13 is very unique magma and has very unique ristic fragments. I think this is from different vent area, from different magmas, but too old to discuss detail. Thank you.
Thank you very much, Hasegawa Sensei. For
Very good question, I think.
Wow. Okay, so I will give this present to the. Thank you very much for your questions. So another question, maybe?
Maybe we can.
If no one asks question, then I will
Later, okay.
ask Sensei. So it is interesting for me about the trend of the caldera formation from west to the east. And it's consistent for all the caldera. I mean, for the Akan caldera itself, it's also trending west to the east. Is there any relationship between, I mean, structural geology, fault, or something that controls the formation of the complex caldera and the whole caldera system in Hokkaido itself?
Yes. It's another good question. So actually, the order of the three small depressions in Akan caldera is not perfectly consistent. So center, west, center, east, and west. And I'm not sure about more older unit. So not necessary to be systematic, but general trend is from west to east. And yes, it's related to the tectonics. So there is a strike slip fault due to oblique subduction. So it makes the space for accommodating large magmas with time of the movement of fault. So, and this trend is very special for Eastern Hokkaido. So Central Western Hokkaido is not so clear system. Thank you very much.
Thank you, Sensei. And may I ask follow-up questions? Regarding the structural tectonics, is there any relationship between the tectonics and the eruption triggers, maybe for the caldera forming eruption, especially? Because we have the case in Sumatra, in Indonesia, that the caldera's volcanoes trend is also following the big structure in Sumatra. So is there any relation between the structure?
I think so. Situation is very similar to Sumatra Island. The scale is bigger in Sumatra, but so oblique subduction and many calderas along the fault. So I think, but I'm not sure about the, you mean eruption trigger by tectonic event. So it's possible. Sometimes eruption triggered by some tectonic movement or shaking the crust, earthquake. But I know another case, some mafic injection, hot magma from the deeper part to the shallower silicic magma chamber. It can also trigger the eruption. So I think triggering the caldera forming eruption is diverse. But tectonic is a very important factor, I think.
I understand. Thank you very much, Hasegawa Sensei, for the explanation. So we have more time for one question, actually. So does anyone have question?
You can get Ibaraki University ball pen.
Ball pen or this
Ball pen or
field note? Yeah. Oh, later, okay. I see. Then I will have more questions. I'm sorry. I can get 3 of them. Yeah. So in the Akan stratigraphy, Sensei said that there are interfingering units with the other caldera. So how to distinguish between the Akan products and Kocharo products and the Kamchatka products?
Thank you. Can I go back to the slide? So actually I skipped the explanation. So it's very good question. こうか。これ。One slide back. Not this one. Next. No. ちょっと待って。これ。Yes, very good question. So, at first, we need to get proximal deposit from Akan and Kucharo. This is definitely from Akan. This is definitely from Kucharo. At first, we need to get. And we make the chemical trend. We analyze it, and we make the chemical trend of Akan. This is Akan. This is Kucharo. And so, for example, this diagram, potassium diagram, So we cannot divide Akan and Kucharo clearly. Blue one is Kucharo, red one is Akan. It's difficult to identify. Mashu is easy. But if I change the element of the diagram, so we can easily recognize this is zirconium, barium zirconium ratio. So Kucharo is high, and Akan is lower. So based on this diagram, even if I find unknown deposit on the outcrop, so once I get the chemical data, so we can easily distinguish Kucharo or Akan based on this diagram. This is a method.
So we need confirmation with another like laboratory analysis, and is it still difficult to differentiate in the field?
Difficult. So it's a question. Very, very difficult. So 20 years ago, the great professor, if I bring professor, oh, this is AK, this is Kucha, oh, AK, Kucha. But that is wrong. Not correct.
Yeah,
so we need to analyze chemistry. This is a true eye to distinguish.
Okay, yes. I understand. Yes, thank you very much, Hasegawa Sensei. So I think we can conclude this first session. So please give another applause for Hasegawa Sensei. And we will have 10 minutes break now. And yeah, we will start around 9:35 to prepare for Aka Sensei's lecture. So please have a good break.
Bring on my talk, please. Slide work is not so perfect. Well, so let's test. So maybe I did this direction. This is not good. So control to this direction. So it's better. Okay. Good. Yeah.
Baik, kepada teman-teman, ini kami masih punya banyak souvenir, ada catatan lapangan dari Geological Society of Japan dan PowerPoint dari Ibaraki University, jadi silakan tidak perlu ragu untuk bertanya ya, karena tidak ada pertanyaan yang terlalu memalukan gitu, semua pertanyaan bisa ditanyakan, jadi silakan percaya diri aja, karena kita sama-sama belajar di sini ya teman-teman. Sayang ini ada bukunya, masih ada 4, pulpennya masih ada 3, begitu. Terima kasih ya semuanya.
so many people going outside. So how if the break time just 5 minutes?
Okay.
So briefly,
Anytime. Just tell me when to start.
Yeah. Maybe we'll start sooner.
Okay.
Get ready.
Okay.
Okay, thank you everyone. So let us continue with our second speaker, Professor Akka Festus Tongwa. Akka Sensei is a visiting professor at Ibarak University. He obtained Bachelor of Science in University of Yaoundé, Cameroon, and then Master of Science in University of Leeds, England, and PhD in Geochemistry at Okayama University, Japan. He worked for many years as a research professor in the Cameroon Ministry of Scientific Research and Innovation. And his research focused on the application of geochronology and geochemistry for basalt, mantle xenoliths, as well as fluid inclusion host volatiles in order to investigate the spatiotemporal variability of sorts, magma plumbing, and mantle dynamics, mainly on the intracontinental Cameroon line. And today, Akka Sensei will be discussing the volcanic hazard and mitigation in Cameroon and how to live in harmony with the volcanoes. So please welcome Akka Sensei.
Good morning. We'll be discussing living with volcanoes and volcanic hazards. This is very familiar with the Indonesian people. They grow and they get old and they go with volcanoes. So what do we know about that? We have an outline here. We'll talk about the volcanoes from a general perspective. That will be the first part of the talk. We'll zoom into Cameroon and see how the volcanic system in Cameroon first compares with the volcanic system in Indonesia and what are the peculiarities of the volcanic system in Cameroon. What is a volcano? A volcano can take different forms, either a mountain peak, stratovolcano, or it could be a crack on the ground, or a hole on the ground. So, but the peculiar thing is, material from the deep part of the interior gets ejected, emitted through this feature. That's where we define a volcano. It can exist on the Earth, planet, or on other planets as well. Where do volcanoes occur? Volcanoes occur in plate margins. For example, spreading ridges like the mid-ocean ridge. An example would be Iceland, East African Rift. Volcanoes occur in convergent margins. This would be the typical case of Indonesia. And you have examples like in the Auditurium, Japan. It's very fast. Wow. Yeah. Examples like the Auditurium, Japan, and Indonesia, the cascades. And then volcanoes also occur in plate interiors. oceanic plates, Hawaii, shield volcanoes, Réunion, and continental plates, Yellowstone, Cameroon. We will see the difference between Cameroon and Indonesian volcanoes to have a better perspective of this geodynamic setting. The Ring of Fire. You are familiar with the Ring of Fire, aren't you? So, world's most active volcano zone is found around the Ring of Fire, and there's a reason for that. This is where most of the places of the world are subduct. Okay, so we are familiar with this area. This is where we are now, right? Up and down sides of volcanoes. So why do we care about, when I say we humans, care about volcanoes? The positive sides of volcanoes, there are lots of things. Volcanoes produce good soil, and some of the world's richest agricultural production comes from volcanic soils. Okay? Volcanoes also have hot springs. In Japan, they are called what, Sensei? Remember? They are called onsen. I don't know about Indonesia, but in Japan, there are lots of onsens in hotels on the mountains. That is one of the benefits of volcanoes because they attract tourism. Volcanoes have also provide peaks for hiking. Observatories are set up on volcanoes, snow and ice spots, and mining and quarrying. The hotel we were living, if you look at the walls, most of the areas around Yogyakarta, the walls are made up of pebbles. And these pebbles probably come from the rivers, which are very rounded, and they bring them down during either pyroclastic flows or lahars. So that's a positive aspect of volcanoes. And then geothermal and hydrothermal energy as well. Most of the world, most of parts of Ireland and East Africa, they use geothermal energy, which is tapped from the ground due to due to volcanic activity. So these aspects explain population clustering. The population, because of these positive aspects, people draw in to areas where volcanoes are built. And with this clustering results in exposure. Because volcanoes are there, and because of the positive aspects, people come in. When people come in, they are exposed to volcanic hazards. Exposure combined with vulnerability to generate risk, volcanic risks, a potential for loss of life, human infrastructure, and livelihoods. Okay, so the vulnerability, how likely a community is will be attacked or will be affected by a volcanic hazard. You know what volcanic hazards are, don't you? For example, lava flows are volcanic hazards, pyroclastic flows are volcanic hazards, ashfall, volcanic hazards, volcano-associated earthquakes are volcanic hazards, okay, lahars are volcanic hazards, tsunamis could result from volcanic hazards. There are a couple of them, okay? So how do we become exposed to these hazards around volcanoes? Downsides of volcanoes, the negative parts of volcanoes. How do these hazards affect people? How many people live around volcanoes? If you have a volcanic eruption occurring in an area which is not inhabited by humans, which has forests. A lava flow, for example, is a volcanic hazard. You can only turn that hazard into a disaster when it has impact on the people, on the community, right? So how many people live around volcanoes? There was some work that was done by Fiere in 2019. So the population distribution in proximity to active volcanoes for 40 years, spanning the period 1975 to 2015. How did they do this? They evaluated human exposure to volcanic hazards and associated disaster risks using available global population densities, okay, and grids and the latest data on recent volcanism, Holocene volcanism. And the volcanoes they used were Holocene, volcanoes with evidence of significant eruptions, and volcanic hotspots of Southeast and Central America. Southeast and Central America, particularly Southeast Asia, is where we talked of the ring of fire, isn't it? So these are the areas where they consider the volcanoes. These are Holocene volcanoes and hotspot volcanoes. This is the way they are distributed. Okay, we are around there, and Cameroon is here. We are going to be able to compare further in the talk volcanoes from around here, around there, and around here. That's the data they got. And I plotted this on a graph. And you can see this is the radial distance from the center of the volcano. And this is the number of people in million. You can see that over a span of 40 years, from 1975 to 2015, the number of people affected by volcanoes has increased. What might be one reason for that kind of increase? One possibility would be the growth of world population, because this number of people is with respect to global population. Okay? The global population is increasing. There's pressure on the environment. There's pressure for land. So people are moving closer and closer to risky areas around volcanoes. Okay? So total population living in proximity of Holocene volcanoes increased steadily for 40 years. That was the result. And then in 2015, more than 1 billion people, 1 billion people is about 14% of the global population at that time, were estimated to live within a range of potential direct impact of volcanic eruption, 100 kilometers. Volcanic eruption can affect people over a range of 100 kilometers or even more. The 1991 Pinatubo eruption, for example, produced smoke which went around the world in the stratosphere, right? So, to be able to reduce the effect of volcanic hazards on humans and the environment, you have to evaluate disaster risk, volcano disaster risk. Volcano disaster risk is perceived in terms of the hazard, volcanic hazard, the vulnerability of the community, and the coping capacity. Coping capacity here would be the resilience. How can people build the capacity, the tendency to be able to resist or be resistant to a particular volcanic hazard? So disaster risk, hazard, vulnerability, coping capacity, and disaster risk management. So a hazard is defined as a dangerous phenomenon, substance, human activity, or occupation that may cause loss of life, injury, or other health impacts, property damage, loss of living. This is United Nations International Disaster Risk Reduction 2009 definition. They have a series of definitions which were established by the UNFID to standardize definitions of words like hazard, like vulnerability, like risk, like resilience, like coping capacity, so that it's standardized across the volcanology community. This is this can easily be located. So when you do disaster risk, we're talking about 4 phases of disaster risk management cycle. When you have a disaster, you can have emergency response. Let's take, I was discussing with Nova Sensei the other day about the 2010 the pyroclastic flow of Pinatubo. So when it happens, you have the disaster risk management unit in the community has to do emergency response, right? Once you do the response, you settle the people, you move up to rehabilitation, okay? And that is the pre-disaster phase, right? And then prevention and mitigation. Once you have settled the people, you want to stop the event happening and affecting the people again, okay? So that is the preparedness phase. And that will be the post-disaster phase. So the 4 cycles of disaster management can be looked at from emergency response, rehabilitation, prevention, mitigation, and preparedness phases. So if you look at the 2010 pyroclastic flow of Merapi, where are we now? Where is the Yogyakarta city now on this phase? We are here, isn't it? We are getting ready for another phase of the pyroclastic flow. If it comes, if we had any casualties here, our ability, the community ability is to try to minimize any losses on human lives or infrastructure which occurred during that time, right? So prevention mitigation is based on identification and evaluation of hazards, okay? So in summary, for this first section of the discussion, a volcano is a place on the Earth's surface or any other planet where molten rock is erupted or emitted onto the surface. Volcanoes occur along plate margins like spreading and convergent margins, and also within oceanic and continental plates. Volcanoes have both positive and negative aspects. That's the interaction of human being with volcanoes and the environment. Volcanoes have both positive, hazardous volcanic areas are likely to become increasingly developed as population pressure intensifies. This raises the level of volcanic risk in communities living around volcanoes, okay? Mitigation of volcanic disaster risks requires evaluating the hazards, reducing community vulnerabilities, and increasing their coping capacities or resilience. That concludes our first section of the talk. So we now move into Cameroon, hazards and mitigation, volcanic hazards and mitigation in Cameroon. Location of Cameroon and physiography. Country data, Cameroon is located in West Central Africa. Okay. Boundaries, country boundaries are here. You have Nigeria here to the west of Cameroon. And you have Chad, Central African Republic, Congo, Gabon, and things like that. The Atlantic Ocean, we have a coast of about 1,600 kilometers. So 28 million, that's about 22% of the population of Japan. Surface area is about that. Population density is 59 people per square kilometer. That's not very big compared to Indonesia, for example, which is what the 3rd largest country in the world in terms of population, with about 158 people per square kilometer. Life expectancy is about 60.3 years, and the literacy rate is about 75. Elevation, the highest point peak in Cameroon is here. The Mount Cameroon region is 4,100 meters high. And it's a volcano, it's an active volcano, as we shall see the talk. Just let me know what the time is, moderator. How much more time I still have? So, Cameroon geomorphic units, we have 3 of them. The coastal lowlands for southern plateau, central highlands, and the northern lowlands, right? So natural resources include petrol, crude oil, natural gas, timber, hydropower, gold, cobalt, uranium. There's a lot of Indonesians in Cameroon commercial business people who work on the timber and mineral exploration. Foreign companies in mining. I brought in this table just to show Indonesia is the fourth largest. This is the number ranked by population. Okay, the first is India, the second is China, the third is USA, the fourth is Indonesia, Japan is number 12, Cameroon is number 51, and Belgium is number 83. You can see the population distribution. For example, for Cameroon, that's the density for Cameroon, the density for America. Okay, America is the third largest country in the world in terms of population. Look at the population density, it's very low. And there is a lot of talk about people going in and out of either country, America, Cameroon, Japan, Belgium, and there's a lot of talk about people giving birth or not giving birth because of the resources. So this is the argument, an argument can be made here that most of the talk is rhetoric. So the Cameroon volcanic line, this is the map of Africa, one of the many swells on the African continent. It has 12 volcanic centers, starting from the ocean. St. Helena is right here, and the mid-Atlantic, this is the mid-Atlantic here. So St. Helena is around here. And if you go there, you see that the volcanoes are aligned about 1,700 kilometers from the ocean, passing through an ocean-continent boundary to the continental sector of the line. It has 12 volcanic centers of alkaline volcanism. Ocean continent boundary is there. It's very unique. Transition from the oceanic lithosphere to the continental lithosphere. Volcanoes around here are very unique in chemistry. No space-time evolution. If you align like this one, the first impression you get will be that we have a space-time alignment. Space-time alignment means volcanoes get older as they move away from a particular area, like in the Hawaiian hotspot, where you have Loihi, which is the currently active Hawaiian volcano, which is the youngest. But as you move away from that center, you have older volcanoes. That's what they call the hotspot, isn't it? Because the continent is moving away from a particular area and generating volcanoes which get older away from the center, right? Last 5 million years have been active. Again, proof that it's not a conventional hotspot. The world's deadliest gas disaster, we shall see. Cameroon contains the world's deadliest gas disaster, which occurred in 1986 and 1984 from 2 lakes. So you can see this is a distribution of the geochronologic data from the oceanic sector, that sector throughout the ocean continent boundary to the continental sector. You can see that the last 5 million years have been active, right? So Cameroon and Indonesian volcanoes, features. For Indonesia, it's found in a subduction zone, okay? But for Cameroon, it's an interplate rift system, right? The number, there are more than 127 plus highest active volcanoes in Indonesia, which is about the highest in the world, okay? And a few active volcanoes in Cameroon. The latest is Mount Cameroon and the lake explosions, as we shall see. Eruption styles are different. High explosivity, VI 4 to 7 for Indonesia, mostly effusive, okay, strombolian effusive activity on the Cameroon volcanoes. Magma types are different, and the acidic high silica content for Indonesia, alkaline basaltic flows for Cameroon, okay? A primary risk, ash pyroclastic flow, tsunamis, lava flow, carbon dioxide gas. And best examples, Krakatoa, Merapi. We are close to Merapi. It's a pleasure for me to be delivering this talk at the foot of Mount Merapi. Mount Cameroon and Lake Nyos. So Cameroon disaster profile, gassy lakes, volcanic eruptions, earthquakes, floods, and landslides. As you see, we don't have lots of lahars, lots of pyroclastic flows. Again, because of the chemistry of the lava, which is different from that of which is found in Indonesia. Then, so advice policy, when we study these hazards, we use the information, particularly from a research perspective, to advise policy on the link between hazard and disaster, and to argue for the government, civil defense, to include our research results in the design of disaster risk management in the country. This is some work that we did. One of the ways to reduce vulnerability and increase resilience is to work directly with the communities. So we carried out community consultations in Cameroon, or in all the regions of Cameroon, using indicators, using indicators like participation, how much does the local community participate in disaster risk reduction? How does conflict resolution matter? How does planning matter? Does the government consider the local communities in decision making when a disaster happens, and so on? And we realized that the disaster affected mostly frontliners, people in our risk zones. See, there are some big disasters which you call major disasters, like you could have an earthquake of magnitude 7. Nobody can hide from that. No news media can hide from that. Everybody knows. But if you go into the suburbs, particularly in Cameroon, you have what they call everyday disasters. When a part of a small mountain slides and probably kills 2 people and clears a house, the media doesn't talk about that. Okay? But if you want to know how many people are affected by a disaster, this is what we call everyday disasters. Everyday disasters happen in local communities which are far away from the prominent news media, prominent decision-making centers. Cumulatively, they cause a lot of harm to the people, particularly to the rural communities, where nobody talks about them. This was the finding that we had from this work. So how involved are the local communities in disaster risk management in Cameroon? To be able to manage disasters well, you need to start from a bottom-up, not a top-down approach. Right? You need to involve the local communities who sometimes use the local traditions, customs, to manage disasters. Because we are coming with a lot of technology now, but these people have lived with these volcanoes sometimes for centuries. They know the methods which their ancestors adopted, which the scientific community seems to be neglecting now. We are advocating that these methods should be used, including in the new technological development, to be able to reduce the vulnerabilities of these local communities. Volcanic eruption hazards in Cameroon. Again, that is Mount Cameroon. Mount Cameroon has 12 volcanic centers. Mount Cameroon has 7 eruptions, within the last century. The last eruption happened in 1919 and 1999 and 2000. These are all Southwest and Summit eruptions. This is the 1999 eruption, which cut a major road in the coastal city. You see, this is lava flow. Okay. Again, as we saw in comparison, how many minutes do I have left? 14. Oh, good. 10. Okay. We saw that because of the nature of the flow, it is future eruptions emit lava flows, which give people enough warning. So you hardly have human casualties in the case of eruptions in Cameroon. Unlike here, when a certain pyroclastic flow, for example, Lahar, could suddenly come and get people off their sleep. Okay, so here we didn't have any casualties, just plantations. Farm plantation was destroyed, but people actually have enough time to move away before the lava comes. Of course, infrastructure is destroyed, but you cannot put a price on human life. That is still 1999. So we made hazard maps of the volcano, and this is the coastal area. The most affected parts are the summit, the southwest, and the northeast. And this alignment is based on the general structural alignment of the Cameroon line. Okay, north 30 east. Most volcanoes and cones on the Cameroon line have the same alignment. Mount Cameroon 2 does. Hazard map. This is one of the cities in Cameroon, the southwest flank. That is the volcano. We have been longing to see Merapi from our hotel since we got here. We haven't been lucky. She's shy. Right? So you can get in Cameroon in the morning, in this town, you can get up in the morning and you can take a good picture of the view with respect to the town. And with community work again around the cities, we use billboards to warn people about the potential hazards. And this work is generated from community-based disaster risk management, community consultations. This is published out here. Earthquake hazards. We use a seismic network around Mount Cameroon. That is where I started work actually when I left university. I was working in a seismological laboratory, setting up these stations around Mount Cameroon. And we were collaborating at that time with the British Geological Survey. We will set up high-frequency seismometers around the volcano. We will telemeter the signals to a central location, collect the signals, and record them on, we used to call them potacoders, pen potacoders. When an earthquake occurs, you can see a signal there. That's an earthquake. And then you will read this earthquake, read the P and S waves, do S minus P, and so on, and then you do the location of the earthquake, and you can see how the epicenters vary with respect to the, if you have a high concentration of earthquakes within a short time, that might be a warning enough that something is happening. And you see the distribution of earthquakes in Cameroon. This is the Mount Cameroon area. The earthquakes around here are volcanic earthquakes. Earthquakes around here are due to faulting. They are tectonic earthquakes. So we had two types of, different types of earthquakes in Cameroon. Frequency distribution. This house was destroyed by an earthquake that occurred before the 1999 eruption. Again, we have there are a couple of publications which deal with this work here. That is Lake gas hazard. Okay, this is Lake Monun, which Asagawa Sensei showed a while ago. We've been working on this lake, but in 1984, gas erupted from this lake and killed 37 people. In Lake Nyos, 1986, 1,700 people died, 3,000 cattle were killed by gas eruptions from these lakes. By 2000, this phenomena were unprecedented in the world. Before this happened, the only known case in the world where gas had emitted from a Moffett. Moffets are not fumaroles, but there are areas around a volcano where gas seeps through quietly. The only other known cases in the world were Indonesia, where some people had been killed by gas erupting from not erupting, actually getting emitted from around a volcano. So 1984 was, 2004 was the degassing. So we inserted pipes inside here. This lake is what, 98 meters? This is Lake Nyos, 210 meters. You insert pipes below the lake, you monitor the carbon dioxide concentration with time, and you can plot that. You see that these are different curves which show the evolution of gas in the lake with time. So you can see whether, you can actually gauge whether gas is continuously getting into the lake and which will eventually erupt. That is the way you monitor what is happening. And then we bring in school children, again, using the community to mitigate hazards. We bring in little children, we tell them about the disasters, and we make sure that they are warned and know enough about these events. Evolution of carbon dioxide before the pipes were installed, and after the pipes were installed, you can see a reduction, drastic erosion. That shows that the experiment was working. Again, we have billboards around these active volcanic areas to warn people not to go too close to the disaster areas. One other problem that we have with Lake Nyos is, apart from the gas, is the dam. We have the gas hazard for Lake Nyos. I just described that. And our approach in the gas hazard issue is using volcanic rocks. Okay, we study the volcanic rocks. We try to work out the plumbing system and try to work out what kind of metasomatism affects the mantle to generate such carbon dioxide in alkaline volcanic systems. Of course, you also have the dam problem. The northern part of this lake is made by a pyroclastic dam, and it is estimated that if this dam fails, water will get out of this lake and flow up to pass beyond Cameroon to Nigeria, and will flow lots and lots of areas. So we worked on the evaluation to know how the rate of erosion of this dam, backward erosion of this dam. We had to date the dam, and there were some conflicting results about the date. And we argued using uranium, thorium, radium methodology that the lake itself was formed about 8,000 years ago, and we were arguing that at the anticipated rate that some other scientists mentioned, there was reason for concern, but no need for alarm. Okay. So I'm not going to bother you with the data there. This is the uranium series that we used to work out the date of about 8,000 plus minus 500 years. This is the dam. If this dam breaks, water from here will flow along the Katsina Valley right to Nigeria. Okay, so the dam was reinforced, engineering. We reinforced the dam to stop a collapse. Flood hazard, landslides. We have landslides, a couple of landslides around and floods around the volcano Mount Cameroon, because pyroclastic material water easily gets soaked into it, so the slopes can fail. And when people build, as we discussed, population pressure because of land, people are getting to settle around hazardous areas. People build along the slopes of the pyroclastic cones, and then when rain falls, these slopes fail, and they can bury houses and also bury people. You see, this is a school which was almost inundated by a flood, okay, close to a city. You see the road, this is the road in Central Plan which was broken. This is flooding, and so on. These things are common, and also common in Indonesia and again, community involvement in the mitigation, very active. Map showing the distribution of floods in the country. Floods affected more than 380 people in Cameroon between 2000 and 2015. In 15 years, we were able to work out 280 people. More than about between 30 and 40% of these were actually deaths. The community affecting you include the people who died and who were displaced, who lost property and lost their livelihoods. In conclusion, the total number of recognizable volcanoes on Earth is about 10,000, with 75% of them based in the Ring of Fire around the Pacific Ocean, where we are now, right? About 5.3% of these volcanoes erupted during the historic times. 500 volcanoes are currently active, with 5 to 10 volcanoes erupting every month in the world. Human interactions with volcanoes are both positive and negative. It is estimated that more than 500 million people are at risk from hazards posed by volcanoes. Volcanism in Cameroon is located within an interplate tectonic system along the Cameroon volcanic line. Volcanic hazard mitigation is essential not only to save human life, but also to ensure sustainable development. Our perspective, the work we are doing now, the work we are working with Professor Sagawa, I didn't go into this. The origin of the Cameroon volcanic line is not known. This is an interplate line, we agree, but compared to typical Hawaiian type volcanoes, where you have space-time variation in terms of age. This is not common in Cameroon. So how does the Cameroon volcanic line originate? There have been 3 hypotheses regarding the age, competing hypotheses for the Cameroon line, intraplate magmatism. Top-down tectonics. All Earth magmatism can be explained by 2 main processes, fluids and melting. This is the view that is held by Professor Iwamori. I was at the Tokyo Institute of Technology last year for 6 months. We were looking at this hypothesis. The other thing is shallow processes dominated by stress, plate tectonics, and fertility variations, mantle convection, okay? And the hot mantle of wellings from deepest mantle subduction. Here is where we are. We are testing this hypothesis using major elements and trace elements in volcanic rocks erupted along the line, the Cameroon line. We are testing what they call potential temperatures, potential melting temperatures. For the MOP, Mid-Ocean Ridge Basalts, Mid-Ocean Ridge Basalts are generated at TPs of around 100, 1300, 1250. But when you have hotspots, which are coming from deeper in the mantle, their TPs are generally higher, up to the range of 1500. So we can be able to test some of these hypotheses based on the determination of TPs for basalts, which are erupted along the line. This is what we are currently working on. So I want to acknowledge research collaboration from Japanese government, many Japanese researchers and students and laboratories. Also acknowledge graduate and postgraduate students in Cameroon, Japan, and the US. We have worked with them for some of these issues in Cameroon. I appreciate Professor Takeshi Asagawa for sponsoring me on this Indonesian trip. Thank you very much, Asagawa-san. So thank you for listening. This is the end of the talk.
Thank you very much, Aka Sensei, for the insightful talks. So we're open for questions first, please.
Thank you very much. As I impressed with your presentation, I'm curious to know to what extent can be the technical success of the Lake Nyos degassing project be sustained or replicated across the Cameroon volcanic line, given the current shift toward decentralized risk management and the increasing encroachment of agricultural population into high risk red zone.
Okay.
Thank you very much.
If I get your question, it is how successful has the Lake Nyos degassing experiment gone? Secondly, what is the effect of population encroachment into the what?
To the shift towards the population, agricultural population into high risk.
To high risk exposure, increase of exposure. Okay.
Yes.
First part of the question. In fact, as I mentioned, can we go back to the slide, please? Let me go. Okay. So how successful has the degassing experiment been? It was pretty, the answer is very successful. But as you can see here, when the experiment started in Lake Nyos in 2001, pipes were inserted to about 200 meters to artificially siphon the gas to the surface. So the gas concentration, the lake is actually stratified. They call it has a hypolimnium and a hypolimnium. So that below about 100 meters of 210 meters, there's no convection below the lake. So it doesn't exchange with atmospheric oxygen. So the carbon dioxide which gets into the lake from the bottom gets stagnated there. So the idea was to insert these pipes so that you can bring up the gas to the surface and liberate it. And it works, because you can see that this is you can see that the concentration of carbon dioxide, okay, the quantity of carbon dioxide with depth was reducing with time, okay? But up to 2017, this area of Cameroon is very, very remote, very remote. Accessibility is very, very difficult. So added to the accessibility problem, there was a civil unrest in the area. So the experiment, because this requires that scientists stay there to monitor the degassing system. So the whole place, a camp was built out there with houses and everything. So we had technicians there actually monitoring on a daily basis the degassing system. But because of the civil unrest, everybody went away. So it has been what? 2015, 2017 to now, 6, 7, 8 years, nobody's been there. So we don't know what is happening in the lake, which is risky. Yeah, with respect to population pressure, getting more vulnerable to hazards, the case in point for Cameroon will be landslides and floods. Because most places in Cameroon have not been mapped with respect to providing the local governments with hazard maps. Even for those that have been, the local government is difficult to implement the research results that we provide to the civil defense authorities. And they might tell you that, okay, this area is hazardous, do not go there and build. But the people who own land in that place will secretly sell land to people. And when they come and build, the scientists don't have the power to tell them, do not do it. It is a complicated system. So as population increases, the vulnerability of the people is increasing. But how do we fight this? Using student projects and consultative and community consultations. We raise awareness of the people to be able to manage be aware first of what hazards they are exposed to and how to manage them when they occur. So yes, population increase is exposing people to more risk. So we are fighting it. The government is not cooperating so much because government is reluctant in incorporating research results into disaster risk management.
Thank you, Aka Sensei, for the explanation. So any follow-up question? So next.
All right, so my name is Iman. I want to ask a question, especially about the population clustering near volcanoes.
About?
Sorry?
About?
About the population clustering near the volcanoes.
Okay.
So of course, there's a very high impact on the lives and the livelihoods of people there. And when we create hazard maps, sometimes when we see the hazard pattern, it overlaps with the current settlements. And that means it necessitates for a relocation away from these hazards. But as we see, because it has already shaped their lives and livelihoods, how do we relocate these people and to create minimal disruption to their lives and livelihoods, and also to emphasize on community resilience?
Wow. How do we persuade people who earn a livelihood from living around volcanoes? How do we persuade them from not doing it because they are exposed to hazards? That's a question, right? I think that is where the disaster management cycle comes in. If you go to the first part of the talk, excuse me. Okay. So, I think the answer to your question will come here. Preparedness. I'll give an example about earthquakes. In Japan, for example, Japan is a very small island in terms of surface area. And Indonesia too, most of the islands in Indonesia are small in terms of surface area. But you live in the ring of fire. So are you going to go away to a different country and live in a different country because you want to run away from volcanoes and hazards? No. The answer lies in the preparation. And you prepare by building up a good and well-funded, decentralized community disaster risk management program. Once you make the people aware, you give the voice to the people. They express their idea on the way that they think they can manage disasters themselves. As I said before, I think you obtain better results than you come in from above with administration and want to impose your ideas on them. So if you collaborate with the people, because these people, as I said before, have some ancient methodology how to manage disasters. It's only recently, within the last, 5-10 years, that this idea of using indigenous ideas to manage disasters has come up. So we incorporate the people because their ancestors have been there for centuries. They know, for example, around Mount Cameroon, the people who live around Mount Cameroon, the indigenous people don't build on valleys. They build on high ground because they know that when an eruption occurs, the eruption is going to follow a valley. Okay? So the creation of hazard maps, the implementation of these hazard maps using the local people is going to help ameliorate the problem. From my perspective, the solution is not running away. Because you don't have enough land. Population keeps increasing, so people have to learn how to live with the disasters. And learning how to live with disasters is bridging the gap between research, between administration, between community consultation, and between the environment. Okay? Yeah.
Thank you very much, Akasensei, for the great explanation on emphasizing the involvement of local communities.
Yes.
So thank you very much for the question, and we will take another question from that side, please.
Okay, thank you. My name is Afrinia. So I want to ask, how does the local knowledge in Cameroon contribute to recognizing early warning sign of volcanic hazard and regarding to reducing the disaster risk?
Say that again, sorry.
Okay. How does the local knowledge in Cameroon?
Lakes, okay.
Yeah, local knowledge in Cameroon to contribute the recognizing and early warning sign of volcanic hazard and reducing the disaster risk.
Lakes, right?
Yeah, local knowledge.
Local knowledge.
Yeah, thank
How
you.
does local knowledge contribute in reducing volcanic risk? Yes, good question. First, we organize community groups around Mount Cameroon, active Mount Cameroon. This was actually a student project, an MSc student project. You do questionnaires and you distribute the questionnaires to everybody living around the volcano, particularly the indigenous people, those whose ancestors were there. And in the questionnaires, you ask them to tell you what happened, the knowledge that they got from their parents to stay away from, for example, the most common volcanic hazard around Mount Cameroon, which is lava flow and gas, okay, and landslides. So once you get this information from them, you then organize community group meetings with the help of the government, the local council. You tell the local council that, yes, we are going to move into this community today, we're going to move into this community tomorrow, and we will be discussing our results of how the knowledge that we got from the community consultations can assist the seismological monitoring. Because I did show you the seismic network that it should be going forward. Seismic network that was set around Mount Cameroon, right? That is government funded. You stay there, you measure you put the seismometers, you measure the earthquake frequency, you measure the depth of earthquakes, and you measure the distribution of earthquakes, and you tell the government if the earthquakes are increasing, you say this here. You say that here, this is the network around the volcano. Okay. And this is the clustering of the earthquake. This was before the 1999 eruption. Once you have an increase in earthquake frequency, you can rush to the governor and tell the governor that we are afraid something is going to happen. So your question is, how does the governor integrate this scientific knowledge into knowledge of the local people to evade destruction from the lava flow? So what we do is, if you can get the site of the volcano where the eruption is going to take place from geophysical information, and also from geophysical information includes seismological information, deformation information, and geochemistry information too. When we measure the springs around the area, you measure the carbon dioxide flow and the gas flow in the springs, all this scientific information combined. Then when you do a hazard map, excuse me, should be behind hazard earthquakes, volcanic eruption. When you do a hazard map like this, you know the areas which are the probability of occurrence of a lava flow covering a particular area over a particular period. But you can incorporate, and what we found actually was that, as I mentioned, the old people in the environment did not build in valleys because they knew, even before the arrival of the scientific knowledge, they knew that when the lava flow occurs, the lava flow actually follows low topography. It goes along the rivers. So they avoided putting their buildings on the valleys. But for now, because the population is increasing and other people are coming to join the local community, the local people are being driven by material money. So they sell the land to the arrivals, to the new arrivals, including selling land which is located in what we call hazardous areas. So the straightforward way of trying to incorporate indigenous knowledge to hazard vulnerability is raising awareness, community outreach. That's the word. Community outreach is very important. So I don't know whether I answered your question, but yeah.
Great, thank you very much, Aka Sensei. So yeah, that questions. Thank you for the good questions. And that questions close this Aka Sensei's talk. So please give another applause for Aka Sensei. And now we will have a short break to prepare for the next talk from Pak Nova. So yeah, let's meet around 10:35. Thank you. All right, let's move on to our third speaker, Dr. Indra Nova Suhendro. So Pak Nova is an assistant professor at the Department of Environmental Geography, Gadjah Mada University. He completed Bachelor of Geological Engineering at Gadjah Mada University and both Master of Science and Doctor of Science at Kyushu University, Japan. Pak Nova research focus on the stratigraphy and dynamics of explosive eruptions. And today, Pak Nova will be discussing about the spatial distribution of quaternary caldera in Indonesia and how the implication of that data for predicting eruption volume. So please welcome Pak Nova.
Thank you. So, good morning, everyone. So I hope you still motivated enough to join to this lecture. And today I would like to talk about a very new research from me. Yeah, it's actually, I just made this research maybe just within 1 month, so it's very new. And I want to publish this result first time here with you guys. And the title is about predicting eruption volume using caldera dimensions. Yeah, so it's morphology. Yeah, it's morphology. Predicting eruption volume using caldera dimensions and its implications for data completion. Yeah, so please note data completion and spatio-temporal distribution of quaternary caldera forming eruptions in Indonesia. So next, I would like to have a brief introduction about the volcanic eruptions. So because here maybe we have various backgrounds, so I would like to start with the type of the volcanic eruptions. So basically, there are two types of volcanic eruptions. The first one is the effusive type, and then the other one is the explosive type. So in the case of the effusive eruptions, the magma chamber decompress slowly, slowly. So as a result, as you know, magma chambers contains gas, volatiles, carbon dioxide, and then H2O, water, sulfur, and anything. So when you decompress these volatile bearing magmas, they turns into bubbles. Yeah. If the decompression rate is small, so you have not so many bubbles. So as a result, the magma ascends slowly. Yeah. And because the gas is poor, so it cannot explode. It cannot fragment it. Yeah. It cannot explode. Just making effusive lava flows or lava domes like such things. And on the other hand, if the decompression rate is high, so the magma can make a lot of bubbles. Yeah, it can generate a lot of bubbles, and then as a result, as a consequence, the magma ascends very quickly. Yeah, very quickly from the 8-kilometer depth up to the 1 atmospheric pressure very quickly, and because it contains a lot of gases, so it will fragment. Yeah, into the pyroclast, as you know, pumices, ash, or scoria, or anything. So this topic will focus on this issue. Yeah, this presentation focuses on the explosive type. So I will not talk about effusive eruptions. Instead, I will focus on the explosive eruption. So please remember, explosive eruption produce pumices because it contains a lot of gases. Next, okay, sorry, look, okay. First thing first, the very normal explosive eruption may be like Merapi or Kelut. This is just a usual case of the explosive eruption where you have a VI3 or VI4 scale eruption. So in this normally explosive eruption, the volcano may form a buoyant plume like this. Yeah. So the plumes rose vertically for about 10 or 20 kilometers. Yeah. In the case of Merapi, the height of the plume reaches 17 kilometers, and after that, the plume dispersed by the wind, so they reach into the further areas. So this kind of eruption can affect some regencies, like it covers the Bantul, Yogyakarta, and then Magelang, Purworejo, and several regencies. And not only pyroxistic faults, but also pyroxistic flows. And in the case of the Merapi eruption, these usually normal explosive eruptions, the pyroclastic flows generally only went into the one side of the flanks, generally, yeah, one side of the flanks like this. So it travels to the south in the case of Merapi, and the runout distance is about 17 kilometers. And as you have known that this eruption has affected us, yeah, really bad, yeah. So it costs about 0.7 billion USD dollars, about several trillion rupiah, yeah. And then the number of fatalities reaches 341 people, yeah. And as you remember, it is already affecting us that much. However, above this normal explosive eruption, we have something extraordinary, yeah, something extraordinary. Beyond that normal explosive eruption, we have caldera forming eruption, which has been introduced by Hasegawa Sensei in the first, yeah. So this is my biggest interest actually in volcanology, caldera. Caldera forming eruption is my passion actually that drives me during the master and PhD, and also Hasegawa Sensei. So a brief introduction. What makes caldera forming eruption so different with the other eruption is its characteristic. So in this case of the normally explosive eruption, like a Merapi, when it erupts explosively, you can still have stratocone. Yeah, the crater is still small. On the other hand, when you have a very huge eruption like a caldera forming eruption, the volcano almost disappears. Yeah. So for instance, is the eruption of the Mount Pinatubo. Yeah, you have the cone. Yeah, you have the cone like this. Initially, it's about 2,000 meters high. But after the eruption, it collapsed. Yeah, it produced such a huge depression. Yeah, like this, So 2.5 times 2.5 kilometers in diameter, which is 25 times of the soccer field. Yeah, so you can imagine the dimension. It's very large. Yeah, imagine that dimension. So it's very large. Yeah. So the volcano collapsed, yeah, and this volcano can collapse because it ejects a lot of magmas, yeah, a lot of magmas ejected within a relatively short time, and this kind of very high decompression rate allows the magma to erupt very explosively and produce these gigantic plumes, yeah, gigantic eruption plumes, and also gigantic pyrocaustic flows. Why I say gigantic is because the plume height might reach about 40 kilometers, 30 kilometers. Exceptional. It's exceptional. And the run-out distance of the pyrocaustic flows may travel up to 20 or 30 kilometers, and especially all over the flanks, not just the southern flanks, not just the northern flank, but all of the flanks. So can you imagine if this Merapi volcano erupt like this? So not only Jogja, but also the Magelang, also Boyolali, and also the anywhere sectors will experience the pyrocaustic flows. So it was very devastating. Yeah, and maybe another famous case is the Vesuvius, Pompeii tragedy. So in that Pompeii tragedy, the volcano also erupt in a relatively similar way with the Pinatubo. So they produce gigantic plumes, about 29 kilometers in height, yeah. And then the runout distance of the pyrocaustic flows travels for nearly 20 kilometers. This is the green polygons. So covering all of the flanks, yeah. And the results, as you have known, maybe the mummified people, yeah. So those people were killed directly by the pyrocaustic flows, which is the most devastating primary volcanic hazards as we consider, as we acknowledge. So many people try to run, from the pyrocaustic flows, but they cannot. Yeah, as you know, pyrocaustic flows move very quickly, 100, 200 kilometers per hour. So it's like riding a very fast motorbike, a sport motorbike. So very, very rapid, very, very quick. So it is the worst case scenario of a volcanic eruption. And the result is nearly the same. So this eruption produced 3.5 times 3.5 kilometers caldera. So you can see the scar here. And after that, this new volcano, Mount Vesuvius, growth inside. Yeah. So this process is repeating. So what is the consequence of the kind of eruption? The first thing first is the ash distribution is extremely large. Yeah. So it not only covers regencies, not just a small area, but it covers nationwide scale, regional scale. The Pinatubo eruption happened in the Philippines, here. But as you can see here, the ash distribution covers Cambodia, it covers Thailand, Thailand, Myanmar, Vietnam, Indonesia, and also Singapore, So it's very huge. Also, the eruption of the Vesuvius in the Italy, the ash covers not only Italy but also the Greece, Greece, and then the Yugoslavia, and the Montenegro, and the other things, nearly reach the Libya. So this means that a caldera forming eruption is a type of eruption that capable of causing a regional scale disruption. So regional, please remember regional. So it not only covers regencies, level kabupaten. It's not that level kabupaten, but it's a level of a national scale, and various nations will affect by this kind of eruption. And this is a kind of imagination, how devastating the eruption is. So if you can imagine that this huge production of ash will cover the entire atmosphere, the entire atmosphere. So you can imagine that such a voluminous ash will block the sunlight. Yeah, it will block the sunlight. And if the volume of the eruption is increasing, so the duration of the ash covering the atmosphere is also getting longer. So as a result, it often causes crop failures, yeah, gagal panen, yeah, crops failures, because the decreasing temperature, like 3 degrees, 2 degrees, is very significant to cause a plant to fail to harvest. And also the ash falling to the rooftops, it causes a load pressure. And if the materials cannot accommodate the load pressure, so it will collapse, roof collapse. It's just one thing. And this is just an imagination of the eruption plumes. So when you have a larger eruptions like this, so this is the Bromo, this is altitude, yeah, kilometers. So generally small eruptions cannot penetrate into the stratosphere. So their shape, yeah, plume shape generally is about nearly circular, yeah. However, as the eruption getting large and large, the volume like the Tambora and Pinatubo, they enters the stratospheric levels, and so the wind wind speed increases, so they can be easily distributed all over the world, yeah. So it's a big consequence, yeah. And what's the worst thing is that aviation will get affected, yeah. Airplanes doesn't like airplane engine doesn't like ash. So as you have ash flying into the atmosphere and it enters the engine of the airplane, it will block. It will cause the engine failure. So the ash will melt. Yeah, will melt inside the turbine. Yeah, inside the turbine, and then they cool quickly. Yeah, and then they cause blockage. Yeah, so the engine cannot move. Yeah, so it's very devastating. So as you know, airplane generally operates here, 10 kilos, yeah, 12 kilos, yeah. So if you have this kind of large eruption, so no airplanes can escape from this kind of eruption, and it covers huge world. And also the runway airport will be covered by the ash, and when such ashes made contact with the like a rainwater, yeah, rainfalls or everything, so they will turn into the sticky, yeah, sticky mud, something like that. So you can imagine that the runway will be very slippery, yeah. So as a result, you can imagine it will cause a very, very catastrophic situation of the world, yeah. Global economic loss. I would say it's like a global economic loss, because, you know, tourisms, and also like a business or everything, it relies on these things, yeah, on these things, yeah. Aviation, yeah. So you can imagine that if this kind of huge eruption happen next time, we don't know when, yeah, we don't know when, but if it happens, you can imagine that the effects to the humans is very, very huge, yeah. And I think it will be larger compared to the 200 years ago, 300 years ago, where our facilities is less advanced than the present day. So keep in mind that. And unfortunately, these examples that I showed you, yeah, Pinatubo and also Vesuvius, is just a small caldera. It's just, yeah. I compared those volcanoes with the Tambora and Samalas. It is the same scale, yeah, very, very same scale. So the scale is very same. So you can see that Pinatubo is already a caldera, but maybe it's difficult to see the crater, right? Yeah, within this picture. And compared to the Tambora, which erupted in 1815, and also the Samalas in 1215, you can already see the dimension. It's larger, significantly larger. About 3 times, 4 times larger than the Pinatubo, which has caused such a huge impact. And this is the relative image, yeah, of the dimension. So this is the Pinatubo caldera, 2 kilos, 2 kilos. This is the Samalas, and this is the Tambora. And then we have Toba, yeah, the greatest of all. I would say this is the greatest volcanic eruption that happened during the Quaternary. Yeah, it happened in Toba caldera, and you can see the dimension. You cannot see the Pinatubo caldera here. The scale is much different. And now Tambora and Samalas looks much, much smaller compared to the Toba. So it's so amazing. I think for me it's quite amazing, yet also quite scary. Yeah, but I feel so amazing because a nature can make such a very, very amazing things. Yeah, so making this very, very huge caldera 100 times 30 kilometers in diameter, and this eruption is very famous for causing a population bottleneck. Yeah, so many scientists believe that this eruption have caused a population bottleneck, so almost ending the people population, yeah, at the time. So As I show you that the dimension of the caldera is vary. Yeah, there are small calderas, moderate sized calderas, and large calderas. And here I show you some examples: Pinatubo, Krakatau, Tambora, Samalas, and Toba. So after the eruption name, I mentioned you the eruption volume. So eruption volume means the amount of the magma ejected during the eruption. So it is in terms of the kilometer cubic. So the Pinatubo eruption ejected about 11 kilometer cubic, so it's VI6, yeah. Krakatau is 21, about 21, so almost 2 times the Pinatubo. You can see that the number of fatalities changed, yeah. Pinatubo killed 900 people, about 900 people, and then Krakatau killed about 30,000 people, and it caused global temperature drop, decrease up to 0.5 globally, yeah. But in the case of the Tambora and the Samalas, the impact is much larger. So VI7, yeah, VI7. So the global temperature drops up to 3 until the almost 6 degrees Celsius. So very, very significant. So you can imagine that if an area is about 0 degrees now, so after the eruption, it turns to minus 6 degrees. So it drops significantly. So the impact to the harvesting, yeah, to some plantation is very huge. And so you cannot make food. So you can imagine the situation, dry and cold situation. And Toba, even though we have no record of the exact number of victims, but it is believed as a reason behind the neural extinction of the humanity. Yeah. So this means that the volume of the information about volume of the eruption, the volume of the ejected magma is very crucial for mitigation. Yeah. For mitigation, volume is a key. Yeah, volume is one of the essential key to for us to for mitigation. And this is I show you the VI, the variation of the VI. So Pinatubo here, VI6. The ash covers already a large area, and then this is Tambora, the green one. It covers almost the entire part of the Indonesia, and the Toba eruption. What caused ash dispersion up to the India, yeah, not only just in the Southeast Asia, but India. And the recent results, they have found that in the nature, they found that the Toba ash also found in the Africa, yeah, in the Africa, Eastern Africa. So the extent of the ash dispersion increased, yeah. So you can imagine the difference. So it is determined by the volume, yeah. So volume is a very important parameter to be known for volcanologists, yeah, for mitigation. Strategies. Okay. However, volume information is still missing. Yeah. So we have, as I counted, yeah, as I conduct some research, I try to look for the geological maps and also the published articles. So I can mention that we have about 47 quaternary calderas in Indonesia. 47 caldera forming eruptions since about 2.0 million years ago up to the present day. Yeah, so this is the distribution of the caldera forming eruptions, but only 13 eruptions have the information about volume. Yeah, so it's less than 50%, even though it's just 25%. So we still have a very big gap in this information. So, and these 13 eruptions like a Toba, Maninjau, and everything, the volume has been determined from the materials. So, as you know, the eruption produced a lot of gigantic plumes, yeah, pyroxenic deposits covering a huge area. So we geologists, yeah, volcanologists, we can measure the volume, estimate the volume by mapping, yeah, conducting mapping. So this data, volume estimate data from 13 caldera forming eruptions was obtained from the mapping. Yeah, mapping. So we visit the places, collecting the thickness and everything, the area. So we got the eruption volume. Yeah, but only 13 data has the eruption volume, and sometimes we often face a very challenging situation because, as you know, Indonesia is a tropical country, so very intensive rainfalls, intensive weathering. So as a result, many outcrops are not fresh. Yeah. So it is difficult to identify, oh, this is a pyroclast or not, this is a soil or not. So sometimes there's a big gap in this condition. So in this situation, I try to develop an approach, yeah, using morphometry data, so using morphology, yeah, dimension of the caldera, to quantify the volume, yeah, to quantify the volume of the erupted magma using morphology, yeah. So in Indonesia, in the case of Indonesia, I simplify the model into two types. Yeah. So first one, the most common type is the stratovolcano cone-shaped edifice. Yeah. So before the volcano collapse, yeah, the shape of the volcano is a stratovolcano. Yeah. And the other type is like in Sumatra, yeah, like a Toba and also the Ranau, we can have a flat or unidentified pre-collapse topography. Yeah. So we don't know whether the volcano was a cone or not. Yeah. Or yeah, can be cone, or it can be just a flat plateau, something like that, or just a basin. So in this case, I name those calderas as a the pre-eruptive condition as a flat or unidentified pre-collapse topography. So when the caldera forming eruption occurred, they eject voluminous magma. So as a result, the roof, yeah, collapse, yeah, the cone or the cone collapse, yeah. So they subside, yeah, and generates pyroclastic flows, yeah, which we map during the field mapping, yeah. So most of the data obtained from this VD, yeah, VD deposits. So most of the data was obtained from the VD. And in this case, I try to observe, estimate the volume using caldera dimension. So caldera dimension means that two-dimensionally you can observe the area, right? Yeah, you can observe the diameter, the axis, the shortest, the longest. You can observe the height, yeah, the depth of the caldera. Yeah, so it represents the it is roughly represents the volume of the ejected magma, because when it collapses, yeah, the dimension of this caldera mimics the dimension of the collapsing roofs, yeah, roughly, yeah. And sometimes we have to put some kind of correction, because in the case of the cone-shaped volcano, you can imagine that the lithics, yeah, so the edifice, not only just widespread to the flanks, but also collapse to the crater. So we have to correct, yeah, we have to correct this inverse cone, yeah, inverse cone, the collapsing cone, with the observed caldera dimension. So maybe I would not explain in detail about this method, but later maybe we can discuss, yeah, because due to the limited time. So anyway, we have to approach. So in this case, in the stratovolcano case, we basically use cone volume, yeah, cone volume of the cone corrected by the volume of the inverted cone, something like that. But in this case, we can use, in the lower case, we can use approach like a rectangular volume, or also ellipsoid, yeah, half ellipsoid volume. Yeah, the result is not so significant. So how was the result? This is the result, the first result, the predicted volume. So the image A in this side, it represents a comparison between the estimated volume from the morphology compared to the estimated volume from the deposits. Yeah. So as I mentioned before, 13 eruptions already have the data, yeah, volume data. So it means that I can compare my result with the results, right? So if my result is same, yeah, my estimation is same with the estimation from the fee deposit, so maybe my equation is good, yeah, hopefully, yeah. So that's why what we call reliability test. If your data matches with the other data estimation, so you have a good data, yeah. So for instance, like this Toba caldera, Toba YTT, yeah. Toba YTT, it ejected 5,300 kilometer cubic volume using a mapping, and using my estimation, I obtained 5,000 kilometer cubic. So not so much difference, yeah. So it means that the estimation using morphology and also the deposit is still consistent, and it is applicable to other eruptions. So because, in my opinion, because it is comparable, so I can try this equation to the unknown calderas, yeah. So to those calderas which still have a missing volume information, like a Tabah Baru or Pasoma and everything, yeah. So I try to do such thing, and we found such a good correlation. So A means the area, caldera area, and O means the observed caldera area. So it shows a strong positive correlation, yeah, with the volume, either DRE or non-DRE. So DRE means compacted volume. So as you know, magma volume expand because during the explosive eruption because of the gas. So DRE means that we corrected the magma volume from the gas phase. But basically they are same volume. Yeah. So both DRE or non-DRE volume shows a strong positive correlation with the caldera area. So this means that the caldera dimension is, yeah, it's a good indicator to estimate the volume. And next, I showed you in the figure D, it's a step diagram. step diagram of the cumulative volume, erupted volume against the time. So here you can see that the, so AP means early Pleistocene, MP middle Pleistocene, LP late Pleistocene, and Hay is a Holocene. So you can see that there are some steps, yeah, the volume, yeah. So sometimes we have an era that produce ignimbrite flare-ups, yeah. So a very productive era when the eruption, when the volcano produce such a big eruption, yeah. And sometimes we have a calm period, yeah, something like that. And if I try to simplify, yeah, the total volume that has been ejected during the Quaternary is about 9,000 kilometer cubic. Yeah, 9,000 kilometer cubic during the past 2 million years. And if we make it average, yeah, divided the volume by the eruption time, we obtain about a 0.005 kilometer cubic per year. Yeah, assuming if the smallest caldera forming eruption generates 2 kilometers cubic of magma like Pinatubo, yeah, so you need 200 years to generate one caldera using this rough estimation. Yeah, about hundreds of years. Yeah, 200, 300, 400 of years. Yeah, within the errors. So I think this means that roughly we will have one caldera forming eruption, assuming a small caldera forming eruption every 200, 300 years. Maybe for example, like the difference between Tambora and Krakatau, less than 100 years, right? Yeah, less than 100 years, and the difference between the Samalas, yeah, with the Tambora is about 600 years. So the error is still within the range of the 100 years. So I assume that if this estimation is correct, so we will experience such a caldera forming eruption within 100 of years. Yeah, within the next 100 of years. And this is the comparison of the physical and chemical parameters of each arc. Yeah, as you know, Indonesia has a lot of arc. Yeah. Sorry, I would like to go back for a while. This one. So just for reminder, here we have Sunda Arc. Yeah, Sunda Arc. I divided into the Sunda Arc in Sumatra and also in the Jawa. And here we have Lesser Sunda Arc. So Lesser Sunda Arc covers the Bali and then the Lombok and also the Sumbawa. And then we have Flores Arc here behind the Timor Trough. And then also we have Banda Arc. We have Sangihe Arc and also Halmahera Arc. So I try to group them based on the arc. And here you can see that it's cut. So this is the depth of the Benioff zone. Yeah. So 100 kilometers below this volcano is the magmatic source. And this 140, 180, 260 something. So in the Sumatra, yeah, the subduction generates caldera mostly within the Benioff zone over 130. Yeah. So depth of the subduction, yeah, that generates magma. So the most productive Benioff zone that produce caldera in Sumatra is about 140 kilometers depth. Yeah. And you see Jawa, in the Jawa island, it is deeper. Yeah. In Jawa, the Benioff zone that generates magma that from calderas is deeper. The source is deeper, about nearly 200 kilometers, yeah, 880, 200 kilometers. And in the Jawa, it's almost same with the Lesser Sunda Arc, like in the Bali, in the Lombok, yeah, and also the Sumbawa. And in the Banda Arc, in the Flores, and the Banda Arc, it's much shallower. Yeah, it's much shallower. Yeah, 100 kilometers, 120 kilometers, and something. And also in the Sangihe Arc. So we can simplify that the depth of the Benioff zone that generates a caldera forming eruption vary between each arc in Indonesia. So it's very important information. And then this is the histogram of the volume. So this is the VI5, VI6, 7, and 8. Yeah. So in Sumatra, there are 2 VI8 eruptions, and which is not observed in other places. Yeah, it's a very important clue because the only volcano that can make such a VI8 eruption is only Sumatra. Yeah. No in Jawa, no in Lesser Sunda Arc and other places. So only in Sumatra. And if we see the other arcs, we have a very similar histograms. So the VEI6 dominates the eruption. So this means that the VI6 is the most common caldera forming eruption scale that produced in Indonesia. Yeah, followed by the VI5, 7, and finally 8. Yeah, and then you can see here, this is the composition. This is the andesites, this is the dacite, and this is the rhyolites. In Sumatra, most of the caldera forming eruptions are rhyolites. Yeah, rhyolites, very, very silicic magma. But in Jawa, it's inverse. Andesite dominates. Yeah, andesite dominates, not rhyolites, not dacite, but andesite. It's very unique. Yeah, it's very unique. And in the Lesser Sunda Arc, dacite dominates the eruption. So dacite. So it's very interesting. And also in the Sangihe Arc, it's rhyolites, and in the other places, yeah, maybe dacite and rhyolite something. But this means by looking at this diagram, so we can think that so this means that the caldera formation sometimes does not require high silica. Yeah, andesite can make caldera formation, and the best thing is that here we found that in the alkalinity, yeah, here is the alkalinity. So low K, low potassium, medium potassium, high potassium, and very, very high potassium sonate. You can see that the histogram is dominated by the high K. Yeah. So caldera forming eruptions always likely requires high K condition, high potassium content. So I can simplify that a caldera forming eruption requires either one, high silica content, even though the potassium can be low, yeah, or two, high potassium without having high silica content, or both. And in this case, the ultimate combo is the high silica and high potassium. Yeah, that's the characteristic that we found. And here is the correlation between the volume, y-axis the volume of the eruption, and x-axis the silica and also potassium. So you can see the strong positive correlation like this. So both silica and both potassium really controls the explosivity. Yeah, and why? Actually, I'm still wondering the answer, but I think now the current simple answer is the magma differentiation. Yeah. So as you know, magma initially are basalts generally. Yeah, low in silica, basalt, very low in silica, and such a low silica condition it cannot accommodate explosive eruptions because they generally easily outgassing, yeah, outgas, yeah, easily make a bubble collisions and everything. So generally rare basaltic eruption producing a huge eruption. And such a hot basaltic magmas will experience magmatic differentiation, so cooling, yeah, cooling. So they will experience cooling. So as they cool, they make crystals, and the silica content in the magma increases. So they can make andesite, they can make dacites, and also rhyolites. And also it requires voluminous injection from the depth magma to obtain a larger volume, yeah, and to keep the heat alive, yeah, heat alive. And if you already have a large magma chamber and evolved magma chamber, you can imagine that the assimilation with the country rocks is also increasing. So you can see that here, the magma initially small. So surrounding the magma, there are cold rocks, yeah, sedimentary rocks, yeah, carbon rocks and everything. And those rocks will melt, yeah, and join the magma, the melt. We call it as an assimilation. So the magma will likely receive input of the potassium from such a sediment, nearby sediments. So as this magma getting large and large, so you can imagine that the potassium content will increase because the amount of the the input assimilation is also increasing. So finally, you have a high potassium content, high silica content, and you have a lot of bubbles and evolved magma. So large magma. So it's very good recipe to produce a caldera forming eruption. And also many studies like Allison et al, they have found that the solubility of the volatiles like CO2 and also the H2O increase by the increasing potassium content. So I think it is very important. And I think worldwide, we have a similar pattern like a high K magma always tend to produce big eruptions. And this is the final diagram that I would like to show, the spatio-temporal distribution of the caldera forming eruptions. So during the early Pleistocene, we have not so much data. Yeah, not so much data because as you know, as the eruption getting older, the data is become more difficult. So I cannot say a lot about this, but the special thing is starting from the mid-Pleistocene. Okay, mid-Pleistocene, yeah. Please look at this for a few seconds. You will realize something to the Holocene. The distribution is moving. Yeah, from the Sumatra here. Yeah, so the caldera forming eruption moves. It moves from Sumatra dominated region and Jawa during mid Pleistocene, and then during the late Pleistocene it moves. And then finally we have here. It's something. Yeah, it's something. This data really tell us something that the next caldera formation will be likely where and how large. Yeah. So that's why geography is very important. Yeah, because you study spatial, and this kind of technique is very important of information for mitigation because you understand the spatial and then you understand where next. Yeah, that's important for mitigation. So by this information, finally, I can conclude that we are likely facing then the next caldera formation about VI6, maybe, and it may be occurred within the next 100 of years, and maybe looking at this spatio-temporal distribution, maybe likely Jawa or maybe Lesser Sunda Arc or the Banda Arc will be the next place, of the caldera forming eruption, and I don't know, maybe Sumatra is possible, but it's now very quiet. So that's all from me. I hope you enjoy my presentation. So thank you so much.
Thank you, Pak Nova, for the interesting presentation. So now we're open for the Q&A session, please.
Yes, please.
Yes, thank you for the opportunity. Hello, Mr. Nova.
Yes.
Could you please elaborate more on how the information of the volume of ejected material can be applied for the disaster risk reduction?
Okay.
Yes,
okay.
I think because it's very interesting. You explain based on your spatio-temporal the ini magmanya apa? Chambernya kan bergeser ya, apa? Kawahnya, kawahnya bergeser ke timur itu kira-kira bagaimana?
Oh, bergeser ke timur?
Ya, dia kan dari barat ke timur. Kira-kira untuk disaster risk education.
Disaster risknya bagaimana? You mean the final slide?
Yes.
Oh, the final slide. Okay.
Thank you.
Okay, thank you, Mas. Mas siapa namanya tadi?
Bagas, Mas.
Mas Bagas dari geologi ya?
Ya.
Oh, Oke, koncernnya share ini.
Kita, Mas.
Okay. Thank you for the question. So, why volume is important? So we'll back for a while because Mas Bagas, in volcanology we have a terminology that we call as a volume explosivity index. Volume explosivity index represents how large the magma ejected during an eruption. And for comparison, I give you this image, like this. So Bromo is VI3, the 2011 eruption is VI3, and this Merapi 2010 is VI4, Agung 1963 is VI5, Pinatubo 1991 is VI6, and Tambora is VI7. So you can see that as the volume increases, the plumb height increases, Mas. The plumb height increases. So if you have a higher plumb height, so the eruption has the ability to enters the stratospheric level, which is very dangerous because stratospheric level has a very fast, rapid wind, strong wind. And once the plume enters this area, it can easily disperse to the larger area. So that's why larger eruption is very dangerous. So once you have bigger volume, the ability to penetrate to this level increases, and also the volume, also the run out of the paroxysmic flows also increases. For instance, like in the Merapi, in the Pinatubo eruption, the paroxysmic flow travels for 20 kilos out the flanks, but the Tambora, it travels 50 kilos paroxysmic flows, and in the Toba, it reaches the Medan, 80 kilos from the source. So you have a very, very difficult situation where you face a larger volume. So that's why volume information is very important. And while unfortunately this volume information is still missing in many calderas. So in order to generate a spatial data set, which is useful to us, so we need to generate that volume first, even though it's roughly. I believe that this error is still under the consideration. Now because we have conducted a reliability test, so the difference might be 1 kilometers, 2 kilometers. It's still okay compared to that we have no data at all, like that. So finally you can see that here spatially we go to the southeast. Sorry, we go to the southeast during the last quaternary, and the VI seems consistent, because we still can produce VI8 sometimes, together with VI7, 6, Regardless the time, VI6 still dominates the eruption, Mas Bagas. So based on my findings, so VI6 always dominates the eruption. So I don't know which comes first, VI5, 6, 7, or 8, I don't know. But the important thing is that VI6 dominates the eruption, so maybe it will be the next, maybe. And you can imagine that VI6 is like Pinatubo. So if such eruption happen in future, it will affect not only Indonesia, of course, but also the neighboring countries. Yeah. But maybe the effect is less significant than the Tambora 1815, which is very, very huge. Yeah, which was very, very huge. And location maybe around here. Yeah, maybe. Yeah, maybe. So that's Mas Bagas. Thank you.
Okay, thank you.
Yeah.
Mr. Nova.
Pulpen belum ya?
Pulpen belum, Kak.
Oh ya, wes.
Thank you very much, Mas Bagas, for the nice questions.
Yeah, thank you. Next.
And now we are open for another question.
Yeah, don't hesitate. Oh, okay, Faris.
Yang merah tadi.
Siapa tadi? Ya, Kak. Tadi Faris sudah ya, ganti dulu deh.
Thank you for the opportunity, and thank you, Mr. Rafa, for the insightful presentation. I want to ask you about how to estimate the volume of magma chamber for the caldera volcano, which was formerly a compound volcano that has many vents, and perhaps create not so round shape of caldera.
Okay, you mean okay. Like akan masuk, like akan sensei. Okay,
Yeah.
so that's very good question. So in some conditions, like sometimes in the old caldera, like Tondano, we have similar situation like sensei's presentation. So nested calderas, and because it's old, 2,000 million years ago, the oldest caldera formation eruption. So there are a lot of post caldera volcanoes, and those post caldera volcanoes covers the makes the appearance of the area and also the depth of the caldera is has error because unrealistic. I mean, the deposition of the post caldera volcanoes covers the actual depth, right? So there are errors. Yeah, there are errors for that situation. So in that case, actually in the manuscript, I wrote that in that kind of situation, we will face such a very huge uncertainties. Yeah, I still do that. Yeah, of course, I still have to measure everything. Yeah, because the reliability is still good. But in some places like Tondano, where is it? Like Tondano, let's see. Even though the caldera dimension is covered by the post caldera, the result is still show a good agreement because I surveyed using the geophysical research. So as you know, as also Sensei showed, so sometimes we cannot only rely on the morphology because sometimes it's covered by the post caldera volcanoes. So in order to solve that issue, we can use geophysical instruments, geophysical papers. They can know the caldera floor, the depth, something like that. Or also sometimes like geothermal studies, yeah, they provide the geological sections. Oh, this caldera is about 10 kilometers depth, something like that. The reservoir, something like that. So it's a very important information to look after. If you have no good surface data, so you need to find more. You have to survive from other studies. Yeah. Using geophysical instruments, also using from the geothermal analysis, or everything. Itu Kanti. Ya. Bisa dipahami ya?
Bisa.
Oke.
Terima kasih, Pak.
Beri dia penghargaan.
Thank you very much for the question. So now we're giving the ballpoint from Ibaraki University. Thank you. So, any other questions? Please.
Sorry, can I have a question?
Okay, thank you very much. My name is Arif. Mas Nova, very interesting idea and very interesting findings. But please explain in more detail how subduction activity and neotectonic control the trend of spatio-temporal distribution of the caldera forming eruption from the western Indonesia to the eastern Indonesia.
Okay, thank you.
Okay, thank you.
So it's a very good question actually, and actually I still have no certain answer about that. But Mas Widi, tolong. Okay. Okay. Oh, nah. So first thing first, the reason why we should differentiate the discussion between each arc is because each arc have a very different geological situation, Mas. First, the subduction rate different. So in this area, in the Sunda Arc area, the subduction rate is about 6 until 7 millimeter per year. Centimeter per year. Like that. Yeah, centimeter. Yeah. But in the Lesser Sunda arc, it is less, yeah, like a 5 something or 6 something. So I think, yeah, such a small, even small difference may affect that timing. Yeah, because the rate of the subduction will implies the volume, the rate of the melt production. So I think the reason why Sumatra was very active at the time, maybe because the subduction rate is higher compared to this area. And also here, maybe it's something that needs to explore. I need to read more papers about that, but I think that's the current idea. And also, I think the crustal density, crustal thickness. So I forgot to show you this, yeah. So this is the crustal thickness of Indonesia from the recent research by the Zhang and Monet. So in Sumatra and Jawa, the thickness of the crust is thick, typically thick, about 30 up to 40 kilometers. But in the Flores, Lesser Sunda Arc, it's only 20 kilos. So very different. So you can imagine that the magma migration, they have a different time to reach the surface, right? So you have a thick, you have a thin crust, so it must affect the timing, yeah, when it erupts. And also here in the Sangihe and also in the Halmahera, the thickness also just 20 kilos. So maybe, I don't know, maybe the reason why now we are facing the timing of this arc being very active is because it's thin. It's now thin. So now it's thin and it's like a timing to erupt more explosive. Maybe that's my current idea. So regional geodynamic really controls that microscale condition. So that's why it's very important for us to understand the geology regional dynamics, yeah, because this important information is very important for understanding such thing. Maybe that's Mas Arif from me. Thank you.
Thank you, Mas, for the good question. So we still have time for one last question.
Tadi siapa ya?
Can I ask a question?
Online ada nggak? Online ada nggak?
Sorry.
Yes.
Siapa itu?
Please. In the online session, we open for the online question, please.
Can I?
Yes, please.
Okay. I'm sorry. I cannot turn on my camera because the connection. Okay. My question is.
Who is this? Sorry.
Sorry, I'm Aldi from Universitas Negeri Makassar.
Okay, Aldi. Okay.
Okay. Okay. My question is from the slide. The title is predicting eruption volume through caldera dimension. If I'm not misunderstanding, how do you predict that? Can you explain it? And does the volume prediction use a remote sensing approach? Yeah. Because I happen to be doing my research, yeah, on Lewotobi laki-laki, and I'm still collecting several sources. Yeah, I think that's all. Maybe can I contact you from outside the forum?
Yes. Please, you can email me or WhatsApp me. It's okay. Yeah.
Okay. Yeah. Thank you. Just that. Please answer it, Mas.
Okay. Thank you, Pak. So the question is predicting the volume. So okay. So I have to go back a little. Okay, so I predict the caldera volume using morphology. Yeah, so morphology means the something that we can observe from the satellites. In this case, you can use anything like just a image, Google Maps image or everything. Yeah, as long as you can measure the area. Yeah, you can measure the area of the caldera. So when you have morphology, you can measure the area, the diameter, the longest axis, the shorter axis, and then calculate the area, and you have the depth, right? Yeah, you have the depth. So the subsidence of a caldera generally mimics the volume of the erupted magma. Yeah. So please look at my figure here. So I showed you some brown shading colors there. That represents the dimension of the observed caldera. Yeah, if this cone collapse, so that means the collapsing, the loss of the magma in the magma chamber is same as the brown shaded area. Yeah, the brown shaded area that phi magma predicted, and it also applies for the another shape of the caldera. VCA is same as the phi magma in the lower image. So that means when we estimates the volume of the magma loss of the eruptic magma from the caldera, it can be, that means that the volume of the caldera observed from the morphology can be used as a proxy to estimate the volume of the magma loss. Yeah, and how I validate my my idea is by doing the reliability test. Yeah, reliability test means that there have been some caldera-forming eruptions which have been estimated the volume using the mapping, mapping like a Toba and then Maninjau, Tondano, and then the Tambora, Batur, and everything. So many studies have provided the volume using the mapping. Yeah. So in this case, I use the morphology data. So I have to compare first, my data from the morphology with the data from the mapping. And as you can see here, the VM, this means that the volume of the magma predicted from the morphology, and the y-axis is the volume of the deposit, estimated from the mapping. So if your data is plotted within this 1.1 line, that means that the reliability is good. Yeah. For instance, the Tambora caldera forming eruption produce 40 kilometers cubic of magma, from the mapping. But from my morphological approach, I obtained 38 kilometers cubic. So not so different, 38 versus 40. It's still within the 1:1 scale. So that means it's reliable. And if you look at to those the other data, like from Naira, Raung, and Batur, Gunung Kawi, Toba, and other things, so they are plotted within the 1:1 line. So this means that this approach is considerably reliable. Yeah. So that's why I use those equations for other caldera forming eruptions. Yeah. Maybe like that, Mas. I hope this answers.
Sorry, Mas Nova, maybe one more question.
Moderator, okay.
Moderator, it's okay?
Yes, maybe short question, please.
Okay. From the explanation, Mas Nova, using the the prediction is using Google satellite imagery. If I have an I have not have Google satellite imagery, maybe can I using another data or like what?
I think as long as you can measure the area, the diameter, the dimension of the caldera, the depth, and then the dimension diameter or anything, so it's okay, I think. And Google Map is just or Google Earth is just one kind of apparatus. You can use another, I think, DM or anything, as long as you have the morphometry data, the value, And sometimes if you have a kind of an ideal caldera shape, like the caldera is filled by a lot of post-caldera activities, so you need to consult with other data like geophysical data to obtain the depth of the magma chamber, the caldera floors and everything. So we need to explore from various data sets, I think.
Okay. Thank you, Mas Nova. Maybe I hope we can still communicate in another media.
I'm open for discussion, so don't worry.
Okay. Thank you, Mas Nova.
Yeah. Thank you. So finish the present.
Perfect. Yes. Finish in time. On time. It's actually on time. Thank you very much for the food talk. So as we approach the end of our talk today, I would like to summarize some key points for each speakers today. So the first talk from Hasegawa Sensei about complex caldera forming. So the complex caldera may be formed from multiple magma chamber instead of a single huge chamber. And the detailed stratigraphy and geochemistry and petrological studies need to confirm all of this formation of the complex caldera. And then the second talk from Aka Sensei is how the special characteristic of each volcano is important to consider the evaluation of disaster risk, and then how involving local communities, indigenous knowledge, traditional customs also is highly important for the disaster risk reduction management. And the last talk from Pak Nova is how is the impact of caldera forming eruption to global disruption, as well as new approach in estimating the volume of ejected material from caldera forming eruption using morphometry. And please give the last round of applause for our speakers today. And here I would like to invite our speakers to receive the souvenirs, special souvenirs from the Faculty of Geography. Oh, no, sorry. Okay, okay. I'm sorry. Yeah, sorry, that's the correction of today's term of reference. Maybe. And then, apa? Invite. Okay. So let us invite all the audience for the photo session.
Maybe standing. Oh, this one. Salah lagi lah. Oh yeah, you remember. GM. Okay, thank you so much. Terima kasih Pak Dedi.
Okay, so once again, thank you very much for all the three speakers for their excellent and informative, insightful presentation. Also, thank you for our audience for the good discussion and for the thoughtful question and active participation. And then this concludes our meetings today. So have a nice day.
Thank you, thank you. Thank you, Prof. Takeshi. Thank you, Prof.
So, yeah, thank you for coming.
Thank
So
you,
we are finished. If you
Mr.
want
Nova.
more discussion with us, so you can just come or anything, or just go home. It's also okay. So it's lunchtime. Thank you. Thank you for coming. Yeah, nice one.